Hi everyone, this is Sharefa ASIRI from King Abdulaziz University. Thanks so much for attending my presentation, which is entitled with Selection of Modulating Functions Design Parameters for Estimation Problems. Here is the outline for my presentation. First, I will motivate the work and then introduce the modulating function-based method. After that, I will give sensitivity analysis study about the method, and then I will propose a strategy for selecting the modulating functions design parameter. And after that, examine this strategy through some numerical simulation. And finally, we will end up with some concluding remarks. As you may know that estimation problems are everywhere in the engineering field, seismic survey, medical imaging, and so on. Whatever the estimation problem you are working on, you need measurements. But the main difficulties, or one of the main difficulties, is say that the measurements are usually noisy. And the problem becomes worse in case you need to differentiate this noisy measurement, as this is a well-known L-post problem. In fact, these limitations are somewhat overcome with the modulating functions method. As with this method, you don't need to approximate the derivative of the measurements. And this factor with other factors gives the method robustness against some noises. In addition, it simplifies the identification problem to the solution of system of linear algebraic equations. Also, it doesn't require the initial values, which are usually unknown, and we don't have to solve the direct problem with the modulating function method. So let's give a quick overview about the method, and we will start by defining what is a modulating function. A function 5x is called a modulating function of order L if it satisfies two conditions. Phi should be continuously differentiable of order L, and the modulating function and its derivatives up to L minus 1 should be 0 at the boundary. So when you have a modulating function, you're ready to implement the modulating function-based method, which can be summarized in the following 4 steps. First, we will multiply our differential equation by a modulating function phi, then integrate over the interval. After that, apply integration by parts, which will transfer the derivative from the measurements to the modulating function. And finally, we will formulate and solve the linear system. Let's see the method, but in our estimation problem we are focusing on, which is the coefficient estimation. Consider the following general form for one-dimensional PDE: Tu plus Pu equals F. F is the source term, T is the temporal derivatives, and P is an operator for the spatial derivatives. And the estimation problem we are focusing on is the following. Given the temporal derivatives at some fixed time instance, we would like to estimate all the spatial coefficients Psj. And the modulating function solution for this estimation problem is given in the following proposition. Let Psj be unknown coefficients in 1, and let's assume we have phi m from m equals 1 up to m capital B, a class of linearly independent modulating function, such that we have the m, or the capital M, which represents the number of the modulating function, greater than or equals to this number, which represents the number of the unknowns, I mean the number of P we have. Then the unknown coefficient can be obtained by solving the system A gamma equals K, where the matrix A consists of submatrices, as here, with the entries given in equation 3. And the entries for the right-hand side vector is given in equation 4, and gamma is the vector of the unknown coefficient. Just notice that in equation 3, we have the derivative for the modulating functions here, the spatial derivative, without any derivative for the measurement u. And this is one of the main features of the modulating function method. Now let's focus on this part, which is the number of the modulating function. As I said, m, or capital M, should be equals, or the minimum of m is equal to the number of the unknown. And in some works, the authors prove that m needs to be increased in some problems. And in one of our previous works, we use the estimator variance as a guideline for selecting this M, and it gives us good results even for M that is far from the minimum. In this work, we focused on the main point, which is why. Why, as we increase M, we have better results. And in fact, we found that this can be explained with what we will call bad and good modulating functions. Let me explain the idea through the figures. The top figure here represents noisy signal. And we can see that the informative part for this signal is here on the first third. The bottom figures represent on the left the modulating function. So I'm constructing 56 modulating functions, and here is the first one. You can see that the modulating function, we can say that has almost compact support on this interval or subinterval. And on the right figure here, I'm showing the product between phi and the signal. Why I'm doing that? Because the matrix A and the right-hand side vector K involves integrals for the product between the modulating function and its derivative with the signal. So now I'm showing, I will continue increase the M, and please keep an eye on this compact support of the modulating function and the product. So as I'm increasing, the modulating function here went to the left, and here is the product. So as we are going to the left, the product becomes better. And as you see here, when the compact support of the modulating function is in a position that is almost around the position of the informative part of the signal, we have a good product. And this is what we will call it good modulating function. So how can we get this good modulating function? Let's explain that on one type of the modulating function, which is, for example, this type, the normalized power modulating function, which has the following form. You can see that by changing the exponent Q1 and Q2, we will have different position for the modulating functions and also different width. Let's focus on this modulating function, the orange one. So it has a compact support or approximately compact support that has center here, let's say it XC here, and it vanishes almost at this green dots. And for the center, this XC, we can express its value mathematically by the following quantity. So as you see that Q2 and Q1 are the main points for the XC. So if we are able to tune Q1, or let's say by tuning Q1 and Q2, we will be able to tune the position of the modulating function. So we use this concept and propose the following algorithm. We propose it as a systematic way for constructing modulating functions that is centered at some position by the user, and to vanish at some certain point. And we examine this algorithm numerically. We try to construct, for example, 3 modulating functions at position 20, 30, and 40, and to vanish at 5, 15, and 30, 5, 15, and 30. And we can see through this figure the reliability of the proposed algorithm. The good thing with that is that give us the idea that we can construct only good modulating function instead of having good and bad modulating function. And this will help us to reduce the system size. However, we have large possible numbers or choices for the XC and X delta. How do we choose the best of them among them? So for that, we propose the following strategy. In fact, in this strategy, we combine the algorithm with the estimator variance to get the optimal choice. As first step, we will implement algorithm 1 to construct IC modulating function based on the candidate values for the center and the vanishing point. And then we will compute the estimator variance of the combination subset XCI. Each one of these subsets will consist of modulating functions of number equals the number we are asking for. For example, you can use the minimum number, which is the number of the unknown. And then we will select the combination subset that give us the minimum variance. This is the proposed strategy, and we can now, we are ready to examine it numerically. So we try to estimate 3 coefficients, alpha 1, alpha 2, and alpha 3 in the 5th order KDV equation, assuming that we have some measurements or its final time measurements in the 5th order KDV. So at first example, we assume that the alphas are equal 1, all of them. So we have this type of measurements, which I'm showing here, the measurement with 0, 5%, and 10% of noise. And based on the measurement support, we used the strategy to construct modulating function. And here is the result for the selection strategy. You can see the estimation errors in percent with respect to different noise levels, starting from the noise-free case up to 10% noise. And we can see the results are very satisfactory. And they are even better to the one we did before when we use only the estimated variance. We do the simulation again with respect using other values for the alphas, which will change the position of the position and width for the measurements. And using the strategy, here is the result. And we can see the results are very satisfactory. So as concluding remarks, at the end, we can say that we propose an algorithm to construct modulating function based on the measurement supports. This helped to reduce the computational load by reducing the size of the algebraic system. We demonstrated the good performance of the proposed strategy numerically, and for future work, we would like to extend the work for real-time estimation. That was all. Thanks so much for attending, and I would be happy to take your questions.